In this video, we're going to take a look at the unit called density. Density is another example of a derived unit. And what density is it's a calculated value, and it's equivalent to the mass of an object divided by its volume. And what's important with density is that it's an example of an intensive or intrinsic property. So we have sort of two different types. We have intensive and we have extensive. An intensive property, it is something that does not depend on quantity, whereas an extensive does depend on quantity. So take, for example, something like gold. Everywhere in the world that you have gold is going to have the same density. It is a property of the material that does not change no matter where you find the material. So a chunk of gold that's found in Wisconsin is going to be the same as a chunk of gold that's found in New York. It's a property of the matter that depends on the matter itself. An extensive property is something that depends on the quantity. So, for example, if I were to find some gold in New York, that gold will have a different mass than gold that is found in Wisconsin, for example, or wherever you find it. So mass, for example, that is a variable that depends on the quantity of material you have. Density, on the other hand, doesn't, because it's what we call a normalized unit. It's the amount of mass normalized to the volume. So in essence, it's an intrinsic parameter of how much material there is per unit volume. So by doing the normalization, by dividing the mass by the volume, we get a parameter that is does not depend on the quantity. So there are a couple of examples of intensive properties. One is conductance. That's another example of an intrinsic or intensive property. And then extensive properties are things like mass. So that will depend on the material. So now let's talk about what are some things. So if the amount of material doesn't affect the density, then what does? Well, there are some things that affect density. And the things that influence density are things like temperature and pressure. So temperature is a really good example. We're going to talk about temperature and its effect on things a little bit more in detail when we get to Chapter 5, which is when we talk about gas laws. But for now, we can kind of start to get a feel for what temperature is. Temperature is a measurement, basically, of how quickly the molecules are moving. So in a solid, in general, the molecules move relatively slowly. In a gas, the molecules move relatively quickly. And in essence, the average temperature is this sort of the average kinetic energy of the molecules that are sort of moving around. Now, when you increase temperature, as the molecules tend to start to speed up, they're going to tend to start to spread out. So in essence, the molecules that are in there that represent the mass are going to start to kind of move apart because they're moving a little faster. And that's going to increase the amount of volume that a given mass takes up. So temperature affects the volume. So when you report a density, that density has to be reported at a specific temperature. And then the same thing with pressure. You can imagine, for example, if you had water and you have a atmosphere above the water. The more atmosphere you have above the water, the more compressed the water gets, and the more you kind of squeeze it in and pack in the water molecules, so the more dense it becomes as you increase the pressure. So temperature and pressure affect density, but the amount of mass does not. All right, so let's talk about units for density. So like I said, density is equal to the mass divided by the volume. And in chemistry, typically this is reported as grams per milliliter. Those are our standard units in chemistry for density, and we're going to work a little bit more with this. So the milliliter, again, is a derived unit of volume, and the gram is just a basic SI unit of mass. So the important unit conversions that are going to kind of come into play here are going to be that for every 1 mil, this is equal to 1 cubic centimeter, and for every 1 liter, this is equal to 1 decimeter cubed. So these are some unit conversions that tend to be important when we're talking about density. Okay, so now let's look at some practice problems that involve density. So this one is our first lecture problem. So you'll notice this as we go on. In the notes and in the PowerPoints, they're going to be a mixture of. It's going to be primarily these lecture problems with a mixture of some slides that'll have steps or different ways of going about a process. So in this lecture problem, we're going to work with density. So this says you need to obtain accurately 30.6 milliliters of ethanol for an experiment, but do not have accurate glassware. You do have an accurate balance. How much ethanol would you have to weigh out? How much ethanol would you have to weigh out to obtain 30.6 mils if the density of ethanol is 0.786 grams per mil? So now we're going to start to work with density in terms of a more functional. In terms of a more functional way of looking at density. So we looked at density in theory. Now we're going to start to look at density as what it tends to be. Density is a new unit conversion. And specifically, what density allows you to do is it allows you to convert between mass and volume. So if you look at the density, this is for every 0.786 grams, we have per 1 mil. So in essence, we can rewrite this as a unit conversion. This 0.786 grams for every 1 mil, which is equal to the density, is just another form of a unit conversion. So we can say that for ethanol, for every 1 milliliter of ethanol, we have 0.786 grams. Now, the reason why I'm pointing this out at this point is because fundamentally this is what we tend to use density for. I mean, yes, we do calculations where we will calculate a density. You'll get a mass, you'll get a volume, and you will calculate a density. We're going to do that in a second. But a lot of the times we use the density just as a unit conversion to allow us to go between mass and volume. And that's exactly what we're going to do here. So let's look at this problem. This problem, and this is what tends to get confusing in chemistry problems. It's very long, and there's a lot of information here. So it says you want to get a volume of 30.6 mils, basically. It says that you need to get this very precisely. So you need to get 30.6 mils, but you have no way to do that. You have no glassware that allows you to measure volume. The only thing you have is a balance. So what the question is basically saying is there a way for you to weigh out a certain amount of ethanol and get a very precise volume at the same time? And that's exactly what it's getting at. So what it's basically saying is it's kind of starting with this idea that you have 30.6 mils. It's saying, okay, I need that. That's what I have to have at the end. And so at the end, the question is well, how much mass would I need to weigh out to get there, right? So it's kind of a little bit backwards. In essence, the end point in this case is we need the 30.6 mils, but as far as the unit conversion is concerned, that's really the starting point because that's what we have. So when I say start, I don't mean we're starting with it in the sense that this is what we're going to start with in the lab. What I mean is that we're going to start with this in the sense that it's the mathematical place that we start in order to work out the other thing. So in this case, we're starting with 30.6 mils, and we need to end with the number of grams. So we need to get that relationship between mils and grams. So how many grams of this ethanol do we have to weigh out in order to get that 30.6 mils? So we have our unit conversion here, which we're going to bring down. And the first thing we're going to do is we're going to put our mils and our grams. And this is the classic setup. This is density as a unit conversion right here. We have a starting point that's in milliliters, an ending point that's in grams. We're going to use the density. So we pull from our density. It's 0.786 grams for every 1 mil. Now that 1 that's in there is sort of implied. Whenever there's a per mil, you can always put a 1 there because that's per every 1 mil, right? So if you divide by 1, you get the same thing. So there is a 1 in there, it's just not explicitly stated. So we put the 1 on the bottom, the 1 mil on the bottom. We put the 0.786 grams on top. And then in your calculator, you're going to do 30.6 times 0.786. And what you're going to get is 24.1 grams for that problem. So the solution to that problem is 24.1. And you'll notice there's 3 significant figures here, so I put 3 significant figures over there. Okay, so let's take a look at the next problem. Okay, great. So this problem has another big long run-up, and then we're going to kind of summarize it into a simpler problem in just a second. So this one says a spacecraft is disabled on a distant planet, SETI Alpha 5. If there are any Star Trek fans out there, you would get that. They need a sample of manganese to restart their engines. All of their specialized analysis equipment is not functioning. A piece of metal is found, and they need to determine if it's manganese. So a little bit hokey, but we'll go with it. All right, so luckily their science officer memorized the density of some common metals. So we give you some densities here. So it says, using a battery-powered balance, they find the mass of the piece to be 0.1456 kilograms. When they add the piece to a graduated cylinder, the volume rises from 1.25 centiliters to 3.27 centiliters. Can they escape from the planet? So this one is one where we're not going to be using the density as a unit conversion. What we're going to be doing is we're going to be calculating the density, and we're going to use unit conversions to get the mass and the volume. So what I did with this was I took this question and I kind of just boiled it down into the most critical part. So let's start to dissect this problem, and the way that I always start any problem is, what is the problem asking us for? So can they escape from the planet? Basically what we need to do is we need to figure out the density here and figure out, is this metal manganese? So in the end, what we got to do is we got to have our density, and we got to have a mass, and we got to have a volume. Now you'll notice that the densities that are given here are in grams and in centimeters cubed. So when we do our work and we plug into our density equation, we have to plug our whatever it is in units of grams and centimeters cubed. Okay, so let's take a look and let's start to dissect this. So we can start with the mass, and that's a relatively simple one. So the mass they give us is 0.1456 kilograms. And like I said, we need our units here for density to be in grams. So we have to do a unit conversion to get us to grams. So if you look at your table, there are 1 times 10 to the third grams is equal to 1 kilogram. So that's our conversion. We get that from the SI unit table. So now we're just going to start to plug in. So on the bottoms we put kilograms, on the top we put grams. So for every 1 kilogram, there's 1 times 10 to the third grams. So when we multiply this out, we're going to get 145.6 grams. And I can plug that in up here. So we've got the first half there. Now let's look at the second part, because I have to do some teaching now about this thing. So it says they add this piece to a graduated cylinder, and the volume rises from 1.25 centiliters to 3.27 centiliters. First thing I want to point out is this is a very unique graduated cylinder because it's graduated in centiliters. So these people don't use the same glassware that we use. Most of our glassware is in milliliters, but obviously we're doing this to make you have to do the unit conversion. Okay, so let's talk about this adding the piece to a graduated cylinder. So what is a graduated cylinder? A graduated cylinder is a piece of glassware. It's kind of this, has a tall thing here, and it's got a little bit of a base at the bottom. And when you put water into it, there are little graduations, and the water level will be in there somewhere. So there's some water that's in there. It starts out at 1.25 centiliters. Okay, and then what they do is they put their piece in, And that piece is going to take up some volume, so the water level is going to rise. So this is kind of the same thing as when you sit down in a bathtub, or if you have a tub of water and you start adding things to it, the water level rises because you're adding volume in there, and the things that you add have a volume, so it rises, so the water level rises. So then it rises to 3.27 centiliters. So this is called displacement. Displacement is when you put something into a water column and the water column rises the same amount of volume of whatever the object is. So let's say that you had a 10 milliliter object and you put that into a graduated cylinder. The water level is going to rise 10 milliliters because that object takes up 10 milliliters inside the graduated cylinder. So if we want to get the volume of the object, what we can do is we can take the final volume minus the initial volume, and that should give us the volume that's displaced by the object. So in this case, we can take 3.27 centiliters minus 1.25 centiliters, and this will give us 2.02 centiliters. And now we have a volume, but the problem is we have to get this volume into cubic centimeters. So let's look at our unit conversions that we have in our palette. So for centiliters, we have for every, so we're going to basically have to do our unit conversions now. So in essence, what we're doing is we need to go from centiliters to milliliters, and then from milliliters to cubic centimeters, right? We know that for every 1 milliliter, there is 1 cubic centimeter. So that's how I knew this. So if I can get to milliliters, I can get to cubic centimeter. So now the question is well, how many centiliters are there per milliliter? So what we have to do is we have to look up those unit conversions. So for every 1 milliliter, that is going to equal 1 times 10 to the minus 3 liters. And for every 1 centiliter, that's going to equal 1 times 10 to the minus 2 liters. So I have to convert my centiliters using these unit conversions. So we have our 3 unit conversions, and now let's start to kind of map this out. So what we have is we have our 2.02 centiliters, and we're going to start to use our unit conversions to get us in the direction we have to go. So we know we have to go from centiliters to milliliters, and then from milliliters to centimeters. Now to go from centiliters to milliliters, we're going to have to go through the base unit. So to do that, and to refresh our memory, for every 1 centiliter, there is 1 times 10 to the minus 2 liters. So centiliters will cancel. And now we look up how we get from liters to milliliters. So for every 1 times 10 to the minus 3 liters, there is 1 milliliter. And now the liters will cancel. And now for every 1 milliliter, there is 1 centimeter cubed. So you'll notice that I am starting to speed up a little bit with these unit conversions, because presumably you're going to start to practice these on your own. And this should start to make sense as to what I'm doing. So in this case, we went through the base unit. We went from centiliters to liters, from liters to milliliters, and then from milliliters to centimeters cubed. And the unit conversions, we had an SI unit conversion, we had an SI unit conversion, and then we have our 1 mil is equal to 1 centimeter cubed unit conversion. So now when you do this out, you're going to get 20.2 cubic centimeters, which we put on the bottom. And if we do our division now, we can divide those two numbers and we get 7.21 grams per cubic centimeter. This is our final answer. And does it check off? Yes. So it is manganese. And if we go back to the original question, just so that you can see where this is coming from, it's basically saying that they need manganese to restart their engines. So the question is can they restart their engines? Because whatever object they found had a density of 7.21 grams per centimeter cubed. So what did we learn in this problem? Well, we learned that we have to be careful about our units. So you'll notice at the very beginning, I set up my density is equal to mass over volume, and I purposefully put down the units that I needed to get me started. And the way that I knew that was because in the end, these densities that we were looking up, the 7.21, 7.87, and the 8.90, were all in grams per centimeter cubed. So that's how I knew that I needed those. Then what I started to do was I took the information that was in the problem. They gave us kilograms, and then they gave us volume in centiliters. And I started to work these toward those units. So I converted the mass to grams. And then I taught you guys about displacement. So this is something that you will see. You're going to do this in lab in your first experiment. You're going to look at coming up with the density of an acrylic slug by displacement. And so 1.25 centiliters to 3.27, we learned that the displacement of an object is equal to the final volume minus the initial volume upon adding it. And then we just used unit conversions to convert to a convenient unit of centimeters cubed. So that covers density, guys. This is an introduction to density problem. Now, let me preface this with, there are a lot of density problems out there. Density represents a very significant portion of Chapter 1, and there are many, many problems that involve density. We can't go over all of them in lecture, so you're going to have to do all of the textbook problems to make sure you understand density.